So, good evening, everyone. So, let's come to our next topic, quantization. In the previous class, we have already discussed about the sampling process, and today we are going to continue with the next step in pulse code modulation, that is quantization. Now, in the previous class, I mean, previous to the last one, we have discussed some of the fundamentals of quantization, and we have seen that quantization basically refers to discretization of amplitude. And for having one PCM signal, it is very important to have a certain finite number of values. So for having finite number of values of amplitude, this quantization is a must. Now, this is what we have discussed in our earlier class, that we are simply trying to represent quantization, the output of quantization as a random variable, which is a function of another random variable, which was the output of the sample signal. So, in the previous to the last class, I told you that before starting quantization, just have a thorough revision of transformation of random variables and addition of random variables, because the operations of random variables basically provide the mathematical basis for understanding the quantization. Now, what quantization is? So let's start fresh. What quantization? See, this was our sample signal M. Now, and this is the discrete sample. Discrete sample V. Discrete sample means after quantization. So M and Ts, we obtained M&Ts after sampling, and let us say, because the output of sampling was simply numbers, that was not waveform. The input signal MT. Now this MT, this was a waveform, which was our input signal or the baseband signal, and this M and M delta T, which are simply equal to summation n is equal to minus infinity to infinity M and Ts delta T minus NTS. Now this signal, this was the sample signal, and this term simply represents the delta function, the impulse function, and basically we are just bothered about this value. This is the sampled value. Now this sampled value can be represented in the form of an array, and once it is written in the form of an array of numbers, we can say that this sampled value is nothing but a random variable. So let us represent this random variable by M. So capital M represent the random variable, and a small m is simply the dummy variable for this random variable. And quantization is another operation which discretizes the signal in signal's amplitude, and the output is again an array of numbers, but the only difference between this m and this, let us represent this random variable by v, and this is small v. The capital V is the random variable, small v is the dummy variable, representing this small v is the dummy variable for this random variable capital V. Now, the only difference between this the array m and the array v is that m can take on any value, any value on the real axis, but v can take on only certain discrete values from the real axis. So we can say that this m is a continuous random variable, and this v, this will be a discrete random variable, right? And this v, this is simply a function of m, And how we are mapping this M to V? Now, let us suppose that this Vk, I think it can be better understood from this figure. Now, suppose that this M was varying between M minimum and M maximum, and we are having 8 representation levels from V0 to V7. Now, for this range of values of M, we are having the element value for the random value will be corresponding to map to, or we can say that these values of M are mapped to V7, and accordingly these values are mapped with V0. So these are these 8 points on the real axis. These 8 points are basically these 8 points belong to the random variable V. So this is basically a many to one function or many to one transformation. Now what happens? So this Vk belongs to this Vk. Now this belongs to random variable V. This is an element of V, and this is also called representation level. Basically, if this V is V0, V1, let's say Vk to V n minus 1, where there are n representation levels. We are saying, or let's say L, because in future we will use L. So let us suppose that there are L representation levels. So these Vk's, these V's, they are simply called the representation levels. Now, if this is a representation level Vk, another representation level will lie somewhere here, Vk plus 1. Then the previous representation level, this will lie somewhere here. Now, how it will be decided that this representation level Vk is to be opted? Now, this Mk and Mk plus 1, these are two boundaries. So, if the value of M lies in this region, then the representation level Vk will be considered, or we can say that these values of M from Mk to Mk plus 1 are mapped to Vk. Now this Mk and this Mk plus 1, these are called decision boundaries. Now these terms are very important. These are called representation. So this Mk minus 1 is also the representation boundary. This Mk plus 1, Mk plus 2 is also the decision boundary. So we can call it a decision boundary, or the decision level, or the decision threshold. Now let us consider a need just for understanding what happens in quantization and what happens after that. How quantization is done. I have taken one input signal. Let's suppose that this input signal is given in red, and these green lines represent different representation levels. So let us assume that these are 1, 2, 3, 4, 5, 6, 7 and 8 representation levels. So let us call these representation levels as V0, V1, V2, V3, V4, V5, V6 and V7. Now these are the sampling instants. So this is 0, this is TS, 2TS, 3TS, 4TS, 5TS, so this is 4TS, 6TS, 7TS, 8TS, 9, 10, 11, 12, 13, 14, 15, this is 15th and this is 16th. So we are representing only the 16 sampling instants. Now what happens here? Now for the sampling instant 0, we can easily see that for the sampling instant 0, this is our sampled value, right? This is our sampled value. For TS, the sampled value is this. For 2TS, this is the sampled value. 3TS, this is the sampled value. Again, this is the sampled value, sampled value, sampled value, sampled value. There. This is our sampled value. So these are the sampled values. So these sampled values, they basically represent M and TS, or these sampled values constitute the random variable M. Now, this sampled value, now see, this is the representation level, okay, and this representation level is V4. So for this representation level, this and this, now this will be the decision boundary. So any value lying between these two lines will be represented by V4, right? Similarly, we can say it like this. For a let me take another color. Similarly, for the representation level V5, this and this would be the decision boundary. So any value lying between this and this will be represented the by the representation level V5, right? Now, at sampling instant 0, our sample value is closer to V4. So the signal will be represented by V4 rather than its original sample value. At sampling instant TS, now the sample value is this, but this is closer to the representation level V5. So we will consider V5 here. For 2TS, it is closer to V6. Similarly, V7 for 4TS, V7 for 5TS. So for 5TS, it will be again V7. For 6TS, it will be V6. For 7TS, it will be V6. Sorry, it will be V5. At 7TS, if it is at V5. For 8TS, now for 8TS it is at 0, so it is lying in between the two representation levels, or we can say that it is lying exactly at a decision boundary. Now if the sample value is same, if the sample value lies exactly at a decision boundary, then it can take any of the values V4 or V3. Now let us consider that it is taking the value V3. This is V5. For 9TS, this is V2. 10TS, this is V1. 11TS, this is closer to V0. Then this is closer to V0. Again, this is closer to V0. Then this is closer to V1. Then V2. Then V3. So this is what our V is. So I think you might have understood the concept of a representation level and the decision boundary. Now, so our sample signal, which we are having the sampled value as indicated by these lines, now they will be represented by these representation levels, and our signal will become like this. So initially we have considered V4, so this will be our level. I think I should take another color. So okay, let me consider black. So it will be V4, then V5, then V6, then V7, 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 then V6, V5, V3, so this is the output. Now these values will represent the output of the quantization. Now for all the further processes, once the quantization is done, now before going through it, let us consider one more point. So after quantization, we can see that there is a clear error which has been occurred due to this quantization process. Now let us consider any random variable. Let us consider, suppose that we are considering this the sample value, the sampling distance 5 ts. Now this was our sample value. Sorry, this was our sample value, and this was our representation level. So this is our quantized value. Obviously, there is a difference between the sample value and the quantized value. Now this difference is known as, this is called the error or the quantization error. This quantization, so if there is quantization, there will be always some error. And this is also called quantization error or quantization noise. Now see, this MNTS, this has been represented by a random variable M. This NQNTS, this has been represented by another random variable L. So this QNTS, this can also be represented by another random variable Q. So this random variable Q can be represented as the difference of the random variables M and D. And in terms of the dummy variables, we can also write a small q is equal to small m minus v. So again, the quantization noise or the quantization error, this can also be represented by another random variable. Now, how the signal is transmitted? Now we are having 8 representation levels. What happens? Let's see what happens. What exactly happens in pulse code modulation? So there are 8 representation levels. Now, for representing these 8 representation levels using a binary digit 0 and 1, we require 3 bits. So we can represent V0 by 000 and V1 by 001, then 010, 011, 100, 101, 110 and 111. So basically these representation levels, they are again encoded using the binary digit 0 and 1, and after encoding, basically these binary digits are transmitted. These binary digits are transmitted, and these binary digits represent the quantized values. So the signal transmitted in PCA, the signal transmitted will be an array of zeros and 1. So it's V4, so it will be 100, then 101, 110, then 111, 111, 111, 110, 101, 011, 010, 001, and so on. So this is the bit sequence. which gets transmitted. Now this bit sequence is transmitted using electrical lines, or you can say that electrical pulses or electrical signals, which we are going to consider in the topic line coding. So line coding basically represents how these electrical signals, how these binary digits or the symbols are transmitted. Now there is one more thing regarding this quantization noise. Now what can be the maximum value of this quantization noise for any quantized value? Now let us assume that this step size is delta. What is delta? Delta is basically the step size. And what is a step size? A step size is basically the difference between the two representation levels. Right. So for any representation level, let's suppose that we are considering representation level V1. So these will be the two decision boundaries, and anything lying between these two decision boundaries will be represented by V1. So what can be the maximum error? The maximum error can be the distance between the representation level and the decision boundary, and this this difference can have a maximum value of delta by 2 this side and delta by 2 this side. So if M and Ts is greater than MQ and Ts, we can say that this error is positive, and if it is less than, if it is lesser, then we can say that the error is negative. So this value, this representation value, the value of this q can lie between minus delta by 2 and delta by 2, right? Or we can also represent it by capital Q. This capital Q is, or the quantization error, this is bounded between minus delta by 2 and plus delta by 2. We will look into it later on when we will calculate the quantization signal to noise ratio. Then we will come back to this topic. Now let's say a few more important points. Now there are two types of quantization. One is called now mid-read and another one is mid-rise. So this is mid-read and this is mid-rise. Now what happens in mid-read, and what are these mid-read and mid-rise types of quantization? Now if 0 is a representation level, right? What happens here? 0 is a representation level. So if 0 is a representation level, then it is called mid-read type of quantization. So we can see that these are the decision boundaries, and for these two, if the input level lies between these two decision boundaries, the representation level is 0, the output is 0. But if 0 is not a representation level, rather it's a decision boundary. In this case, 0 is a decision boundary. So if 0 is not a representation level, if 0 is not a representation level, then it is called mid-rise type of quantization. Like in the previous example, we have seen that we were having a mid-rise type of quantization. 0 was not a representation level, right? So suppose that we are having the input signal. If we are taking mid-read type of quantization, then this will be our representation level, and these will be other representation levels. Right. So this will be a representation level, this will be, and there will be other representation levels. So 0 will be a representation level. But in mid-rise type of quantization, 0 won't be a representation level. See, we are not considering 0 as a representation level. Rather, 0 is a decision boundary. Actually, it doesn't make any difference while calculating the peak SNR or signal to noise ratio for quantization or calculating quantization error. But you must know sometimes in the question, whenever we go for the gate questions, in question it's mentioned whether it's mid-rate type or mid-rise type of quantization. So this is basically a graph representing the quantization noise. You can see that this quantization noise, this is lying between. Now this quantization noise, this is lying between minus delta by 2 and plus delta by 2. So this is minus delta by 2 and plus delta by 2. Now let us calculate quantization noise and SNR. So how can we calculate, how can we represent quantization noise mathematically? Now we have seen that Q is equal to M minus V, right? Now let us assume that M is a zero mean. M has a zero mean. So this implies we will also have a zero mean, and if both M and V, because V is a function of M and such that V is obtained from M, V is the quantized output of M. So if M has a zero mean, we will be definitely having a zero mean. Now if both M and V have zero mean, then mean of Q will be also equal to 0. Now if mean of Q is equal to 0, this means that power in quantization error, PQ. Now let us consider this is quantization noise power. And when I am saying noise power, it means average noise power. So this PQ, this will be simply equal to mean square value, and this is simply equal to the variance. If mean is 0, mean square value is equal to the variance. Now how can we mathematically model this Q, the quantization error? Now this Q, this can take any value between minus delta by 2 and delta by 2. We are not sure. So we can represent Q by uniformly. This can be represented by a uniformly distributed random variable. Random variable with mean is equal to 0. So we can represent the PDF, probability density function for Q, like this. So this is uniformly distributed between minus delta by 2 and plus delta by 2. So what will be the height of this uniformly distributed function? Obviously the area under the curve must be equal to unity, and if its span is delta, so its height must be equal to 1 by delta. So I think you are aware of probability density function of any random variable. Now what will be EQ square? Now this is equal to summation minus infinity to infinity Q square into PDF dq. Now this is limited between minus delta by 2 to delta by 2 Q square, and what is this? It is constant. It says a constant value 1 upon delta dq. Now solving this, you will get, I am not doing all the mathematics, it is simply equal to delta square by 12. So if signal power is equal to P, this implies what is SNR? SNR for quantization output. Now this is equal to signal power upon noise power. So this is equal to P upon delta square by 12. Right. Now how can we calculate delta? How can we calculate delta? Hmm? Now let us suppose that there are L representation levels. So let us suppose that this is minus M maximum and this is plus M maximum, and there are L representations. So what is the total span of this signal? Total span is equal to twice of M max, right? So total span is equal to twice of M max, and if there are L representation levels, then what will be delta? Simply equal to total span of the signal divided by total number of representation levels. So this delta, this is simply equal to twice of M max divided by L. And what is L? L is total number of representation levels, and let us suppose that there are R bits per representation level. Like in the previous case, we have seen that there were 8 representation levels and there were 3 bits. So if there are R bits, then L is simply equal to 2 raised to power R, right? So we can write it like this. So this delta is equal to twice of M max divided by 2 raised to power R. So we can write it over here. So this will be equal to P uh, that I should write 12 P. This 12 will come in numerator, and delta square is simply equal to 4 M max square divided by 2 raised to power 2R. So this 2 raised to power 2R will come in numerator. So we can write it like this. SNRQ, now this is equal to 3P upon M max square into 2 raised to power 2R. So this is the general expression for SNR for any signal. Now let us consider an example where we are considering a sinusoidal modulating signal. This means that we are considering MT to be sinusoidal, and let's suppose that this is our sinusoidal signal as a function of time, and let's suppose that AM and minus AM are two limits of this signal. So what will be the signal power? Signal power is simply equal to AM square by 2. What is M max? M max is equal to A. Now we were having the formula for SNR. This formula was 3P upon M max square into 2 raised to power 2R. Now substituting the values of M max and P, we will get 3 into AM square by 2 divided by AM square into 2 raised to power 2R. So this AM square will get cancelled out. So this is equal to 3 by 2 into 2 raised to power 2R. Now in log, in decibel scale, in dB, 10 log to the base 10 is SNR. This is simply equal to 10 log to the base 10 1.5 plus 2R into 10 log to the base 10 2. Simplifying, you will get This is simply equal to 2 into 10 is 20. Log 2 is 0.3. So it is 6R. And this is equal to 1.8. So this is simply equal to 1.8 plus 6R. So if R is equal to 3 bits, we can see that this SNR is 19.8 dB. If it is 4, then it will be 25.8 dB. If it is 6, then it is 37.8 dB. If it is 8, then we can see that it is equal to 49.8 dB, and so on. So for every bit, SNR increases by 6 dB, and by 6 dB means that is it becomes 4 times. So the SNR is increasing by a factor of 4, or it is increasing by 6 dB. Now let us come to non-uniform quantization. See, in the previous case we have seen that for quantization the step size was constant, was uniform. Now if the step size is same, if delta is same, or if delta is constant, that is constant. If delta is same for all representation levels, or if it is constant, then it is called uniform quantization. But if this delta, the step size, delta is varying between different representation levels, then it is called non-uniform quantization. Now what is the meaning? Why we require non-uniform quantization? See, uniform quantization was very simple. We have already seen it. But why non-uniform quantization is required? Now this is required because the amplitude level of most of the signals. See, most of the times we see that the amplitude level of the signal lies closer to the origin or zero, and for a very lesser period of time it goes to its peak values. For example, in the speech signals. Now in speech signals, most of the times our voice is weak, sometimes only it goes loud. Now if we are considering uniform quantization, then what happens is that we are having equal step size, right? And practically it has been observed that uh, if the voice is weak for 1000 times, then it will be loud only for one time. So the ratio of voice going weak and loud is around this, approximately it's roughly 1000:1. Now if we are having a larger step size, then we may miss out some of the information for the weaker signals. And having, see, we are having a lot of information in this range, still we are having very few representation levels, then it is the possibility, there is always a possibility that we are going to miss out some of the information. Again, here we can see that we are having very lesser information in this range, but for the amount of information what we are having over here, the step size is large. So the step size is small, sorry. So we can see that there is a lot of redundancy. So the problem here is that if we are having a smaller step size, then we can miss out some of the information for the lower signal, for the weaker signals, and for the higher signals we will simply add redundancy. Now there are two possibilities, there are two solutions. Either we can increase the number of step size throughout. Now if we are increasing the number of if we can decrease the step size throughout. If we are decreasing the step size, then definitely we are going to increase the representation levels, and if the number of representation levels are increased, then the number of bits are also increased. And if the number of bits per representation level or per symbol is increased, then the total number of bits which is going to be transmitted will increase, and this will put up, or we can say that our bit rate will increase, and once the bit rate is increased, this will put up a pressure on the capacity of the channel. So for transmitting higher bit rate, we require a channel with larger bandwidth. So for reducing the requirement of larger bandwidth, or for reducing the transmission bandwidth of the signal, the number of bits must be smaller. So there is a trade-off. We cannot have very lesser number of representation levels, otherwise we can there is always a possibility of missing out some of the information. On the other hand, we cannot have a very large number of representation levels, otherwise the bit rate will increase, putting up a pressure on the transmission bandwidth. So this was one of the possibility which we have ruled out, that we cannot simply keep on increasing the number of representation levels to decrease the step size. Now the second possibility is non-uniform quantization. In non-uniform quantization, we take a smaller step sizes for the weaker signal and larger step size for the louder signal. Now in this way we can have a sufficient number of representation levels without putting up much pressure on the number of required bits for representing the representation level. So in non-uniform quantization, what we generally do is that we use more number of, so in non-uniform quantization we use smaller step sizes for weaker signal and larger step size for louder or stronger signal. Now how it is accomplished? Now this is done by compressing the signal first. For this, what we do, we are having one message signal empty. We simply compress the signal. We compress the signal before quantization. The signal is first compressed and then signal is quantized using a uniform quantizer. Now, how the signal should be compressed? The simple rule for compression should be such that the signal having the lesser value, the weaker signal, must not be compressed, or if it has to be compressed, then the compression must be small, and there must be more compression for the higher values of the signal or for the louder part of the signal. So how can you suggest any of the mathematical function where compression which can be used for this compression, and such that the compression for the lower values is smaller and the compression for the larger values is larger? And the only mathematical function which can do such operation is the log function. So this logarithmic operation can perform. See, you can see that what is log of 1? This is 0. Log of 10, this is 1, and log of 100, this is equal to 2. So from 1 to 10, you are just increasing 9. You are just going for an increment of 9, and in decibel scale, the increment is just 1. But from 10 to 100, the increment is 90, and uh, again the increment of the logarithmic scale is just 1. So for the lower values, the separation is small. For the higher values, the separation is large. So basically, these are the two quantization laws which are most famous practically. One is called the mu law, other one is called the A law, and both are logarithmic laws. Both are logarithmic. So we can see that for the lower values, these are the normalized input and the normalized output, normalized such that the maximum value is 1, and this is we have just considered the magnitude, the mod of m and the mod of v. So as the signal is quantized for the positive half, in the same way it is quantized for the negative half. So if we are not considering this mod, then we will have to draw the graph for the negative part as well. So that will be simply the exact replica of what we are getting for the positive values. So for the lower values of m, you can see from here, for the lower values of m, you can see that the graph is almost linear for both a mu law as well as a law. The graph is almost linear for the lower values of m, but as the values of m increases, the graph becomes curved, or the signal is getting compressed. So these are the different values of mu. This is the relationship between mu and m and v for different values of mu. Here also, this is a function between v and m, mod of v and mod of m, with a as a parameter. So these are the different values of a, and for these different values of a, we are getting different curves, and we can see that the signal is getting compressed. The larger value of the louder part of the signal, or the larger values of the signal, are getting compressed. So in the next class, we will do gate problems from sampling and quantization. Please try to attend that class, because I have just picked randomly. I have picked 12 questions from gate examination, and they are really good questions. So I am going to do those questions in my next class. So it's over for now. Have a nice day.